Welcome to the deep dive. Ever wonder how airplanes manage to fly safely, through clouds and in really low visibility?
Yeah, it seems almost magical sometimes, doesn't it?
It really does. But it all comes down to this incredible, often unseen infrastructure,
It
the air traffic control system.
it's like a finely tuned orchestra, as you said. Everyone needs to be playing their part perfectly.
Exactly. And based on these FAA materials we've got here, we're going to pull back the curtain a bit.
Yeah, look at the essential elements that make instrument flight possible. The radios, the ground facilities, the procedures, even the language they use.
Our goal for you today is pretty simple.
Yeah.
We want to help you make sense of how pilots communicate and work with ATC during instrument flight,
Hopefully you'll have some of those aha moments where the whole process just clicks.
and understand the vital role this system plays. We'll be drawing straight from official FAA documents for this. Okay, ready to dive in?
Let's do it. Let's start with the pilot's primary link, right? The communication equipment.
The radios.
Exactly. For civilian pilots talking to ATC, the main channel is the VHF radio band. Specifically, 118,000 to 136.975 millihertz.
So a dedicated slice of the radio spectrum just for aviation talk.
Pretty much. Keeps things separate.
But it's not just about tuning into that range, is it? Your radio needs to be able to, handle the specifics.
Precisely. To really use the whole system effectively, aircraft radios need what's called 25 kilohertz spacing.
Okay, what does that mean in practical terms?
It just means more channels fit into that band. It lets controllers assign really specific frequencies, like, say, 134.575 millihertz instead of just 134.5 or 134.6. More precision.
Gotcha, more available slots. But what if ATC assigns a frequency your older radio maybe can't select?
Yeah, that can happen. The FAA guidance is clear. You just need to speak up, tell them you can't select that frequency, and ask for one you can use.
Simple enough. Don't just stay silent.
Never. And a typical setup in the cockpit, like you see in Figure 2.1 in the materials, usually has separate communication comm and navigation NAV transceivers.
Two radios, basically. One for talking, one for navigating.
Kinda, yeah. Often combined in modern units, but conceptually separate functions.
Now, you mentioned how we talk, simplex and duplex. Can you break that down?
Sure. Think of simplex like a walkie-talkie. Press to talk, release to listen.
Right.
Only one person at a time.
Right. Most ATC comms are like that.
The vast majority, yes. Duplex is more like a phone call you can talk and listen simultaneously.
Okay. When would a pilot use fiplex?
The classic example in the sources is talking to a flight service station, an FSS. You might transmit to them on one frequency, say 122.1 megahertz, using your comm radio,
Okay.
and listen for their reply on a completely different frequency, often a VOR navigation frequency tuned on your NAV radio.
Oh, I see. Transmit here, receive there, simultaneous.
Exactly. Now, managing all this audio, which radio you're listening to, which one you're transmitting on, that's the job of the audio panel.
Right. Figure 2.2 shows one. It looks like more than just a volume knob.
Oh, definitely. It's the central hub. You select which receivers you want to hear, maybe PM1, COM2, a Navade identifier, the intercom.
Adjust volumes for each.
Yep, and critically, you select which radio transmits when you key the mic. And speaking of mics, the FAA strongly recommends headsets with boom microphones.
Like the one in Figure 2.3. Why is that so important?
It's all about clarity. Putting that mic right next to your mouth drastically reduces background cockpit noise engines, wind.
Makes your transmissions much clearer for ATC.
Exactly. And good headphones help you hear them clearly, too. So a good headset isn't just comfort, it's really a key piece of safety gear.
Makes sense. Now, the ability to switch between KM1 and COM2, when's that come in handy?
It's super useful. It lets you monitor one frequency while actively using another. Like you could listen to the ATIS broadcast on COM2.
ATIS being the airport information, weather, runway.
Right. You listen to that on COM2 while you're talking to the approach controller on COM1. You get the info without cluttering the main frequency.
Or checking an evade.
Yeah, exactly. Monitor the Morse code identifier on a VOR using your NAV receiver audio through the panel while still talking to center on FM1. It confirms you're tuned to the right station.
And tucked away in these audio panels is usually a marker beacon receiver.
Often, yes. Marker beacons are simple. They operate on one fixed frequency, 75 megahertz, no tuning needed.
So what do?
They give you an audio and visual cue when you fly directly over specific points on certain instrument approaches, usually the outer, middle, and sometimes inner markers. Helps with situational awareness during the approach.
And finally, on equipment, these integrated GPS comm units, like in Figure 2.4, they seem pretty common now.
They are, and they really streamline things, combining GPS navigation with the communication radio.
The cool part seems to be the automatic frequency selection.
It is.
Yeah.
Because the GPS knows exactly where you are, it can look ahead in its database and automatically put the correct frequency for the next sector or facility into the standby position on your comm radio.
Reduces workload quite a bit, I imagine.
Definitely. Helps ensure you're talking to the right controller at the right time. Okay, so that's the talking part. How about how ATC sees aircraft? Radar and transponders.
Right, radar. We all kind of picture the spinning dish. What's key for pilots here?
The big distinction is primary versus secondary radar. Primary is the old school way. Send out a pulse, get a faint echo back from the aircraft's skin.
Just shows something is there.
Pretty much. Limited info, secondary radar is much better. It relies on the transponder in your aircraft.
The box we put the squawk code into.
Exactly. The ground station sends an interrogation signal, and your transponder actively replies with a coded message.
Giving much more information.
Way more. Your identity, usually your altitude if you have Mode C, and it's a much stronger, more reliable signal. It's really the foundation of modern ATC. Primary is like seeing a shadow. Secondary is like the plane waving a bright flag with its name on it.
And that's squawk code. The 4-digit number ATC assigns.
Yep. That's what links your specific radar blip to your flight plan in their system. And then there's the ident function.
Squawk ident. What does pushing that button do?
It makes your specific radar target momentarily bloom or flash on the controller's screen. It's how they positively identify you, especially when you first make contact or if there's confusion.
And the FAA says always verbally confirm after you hit ident or change your code?
Good practice, absolutely. Niner Echo X-ray identing just closes the loop.
Okay, and Mode C, that comes up a lot.
Mode C is all about automatic altitude reporting. If your transponder has it and it's set to ALT mode, it automatically sends your pressure altitude down to ATC with every reply.
So they see your altitude right there on their screen.
Correct. Hugely improves safety and efficiency, reduces the need for constant verbal altitude reports.
And crucially, adjusting your altimeter setting in the cockpit. That doesn't change what ATC sees, right?
Not at all. The transponder sends raw pressure altitude, reference to the standard pressure level of 29.92 inches of mercury. The controller's computer corrects this based on their local altimeter setting to display your approximate indicated altitude, but the raw data transmitted is always standard pressure altitude.
Got it. Consistent reference point. When do you have to have the transponder on? And with Mode C?
Well, if you have one, it generally needs to be on anytime you're in controlled airspace. Mode C, the altitude reporting part, is specifically mandatory in Class A, B, and C airspace.
And around busy airports.
Right. Also within 30 nautical miles of the primary airport in Class B airspace, from the surface up to 10,000 feet, and above 10,000 feet everywhere, except below 2,500 feet AGL.
So pretty much always advisable to have it on in squawking altitude if you have it.
Absolutely, unless ATC tells you otherwise. It helps everyone see and avoid each other. Okay, so we have the gear. We know how ATC sees us. Let's talk about the actual the procedures and language.
Yeah, this seems critical. Having the equipment is one thing, using it correctly is another.
Totally. Clear, standardized communication is paramount for instrument flight safety. The FAA really drills down on this.
And the main reference guide for all this terminology is?
The Pilot Controller Glossary. It's right there in the Aeronautical Information Manual, the AM. It's basically the dictionary for ATC speak.
Defines all the terms.
Exactly. And it gets updated twice a year, so pilots really need to review it periodically to stay current. New terms get added, things get clarified.
And because so much involves letters and numbers, clearances, altitudes, frequencies, there's a standard way to say them, right? The phonetic alphabet.
Absolutely essential. Figure 2.5 in the materials shows it Alpha, Bravo, Charlie, Delta, and so on. And specific pronunciations for numbers like tree for 3, 5 for 5, niner for 9.
Why is that so important?
It eliminates ambiguity. Over a crackly radio, B could sound like D or E or P, but Bravo is distinct. Same with numbers. It prevents potentially disastrous misunderstandings and clearances.
And the controllers, they're working from a script, too, in a way.
Pretty much. They follow very precise phraseology outlined in their own rulebook, the Air Traffic Control Manual, FAA Order 7110.65.
So pilots can learn to recognize patterns.
Exactly. Once you fly IFR a bit, you start to recognize the standard phrases controllers use in different situations, issuing clearances, vectoring, handoffs. It helps you anticipate what they're going to say and process it faster.
So best way for pilots to get good at this, besides just doing it?
Well, the FAA suggests studying the examples in the AM. Listen actively to ATC Communications. LiveATC.net is great for that. Hear how others do it.
Learn from observation.
Yep. And crucially, never hesitate to ask for clarification. If you didn't understand something, just say again, or ask them to repeat it using plain language if needed.
No shame in asking.
Absolutely none. Safety depends on understanding. It's a cooperative effort. Pilot and controller working together. Okay, now we know the language. Let's look at the actual places where this communication happens, the different ATC facilities.
Right, it's not just one giant room somewhere. There's a network. The materials mentioned flight service stations, towers, TRACONs, and ARTCCs. Let's start with FSS.
Flight service stations, or FSS, often your first point of contact. They handle a lot of pre-flight and some in-flight services.
Like weather briefings.
Definitely. Comprehensive briefings, weather, NOTAMs, airport conditions. They also file your flight plan into the AT&T system.
Can they give you your clearance?
They can relay clearances, especially if you're at an airport without a tower. They issue NOTAMs, broadcast weather. They're kind of the information hub before you get airborne and sometimes while you're flying.
Sounds like a vital resource. What else do they offer?
Well, there's en route flight advisory service, EFSS, often called Flight Watch. That's specifically for in-flight weather updates relevant to your route. Some FSS also take weather observations, and they can help coordinate with customs for international flights.
A lot of functions. How do pilots reach them?
The easiest is the phone, that 1-800-WX-BRIEF-EAF number. In the air, you can use radio. Sometimes direct to the FSS, or often through remote communication outlets, RCOs.
Unmanned radio sites linked to the main FSS.
Exactly. Or ground communication outlets, GCOs, which let you use your aircraft radio to basically make a phone call to FSS or ATC from the ground at some airports. And that duplex communication via VORs we talked about earlier.
Where do you find all these frequencies?
The Airport Facility Directory, the AFD, is the primary source, also shown on sectional charts.
Now, when you file that IFR flight plan with FSS, where does it go?
The briefer enters it into the main computer system of the Air Route Traffic Control Center, the ARTCC, that covers your departure area.
The center.
Right. The center's computer processes it and generates flight strips. Figure 2.6 shows an example. These strips, usually electronic now, get distributed to all the relevant controllers.
Like the tower, the departure controller.
Yep, and the first en route sector controller. This usually happens about 30 minutes before your planned departure time.
And if you don't take off,
the flight plan eventually times out. If you don't activate it by contacting ATC, it gets automatically canceled, usually 2 hours after your proposed departure time. They assume you didn't go.
Makes sense.
Yeah.
What about getting your clearance from an airport without a tower, maybe out in Class G airspace?
Good question. You'll typically get your clearance from FSS, either radio or phone, before you start up. It often comes with a clearance void time.
Meaning you must take off before that time.
Exactly. If you miss the void time, the clearance is invalid and you have to get a new one. Or sometimes you get a release time, meaning you cannot take off before that time.
So timing is critical.
Very. You need to be ready to go when you get that clearance. Okay, moving up the chain, the Airport Traffic Control Tower.
The tower cab, we see them up there. What's their role in IFR flights?
In a busy tower, you might have different people doing different jobs, often a dedicated clearance delivery controller. Their frequency is in the AFD and on approach plates.
They give you the actual IFR clearance.
Yep. If there's no dedicated clearance delivery position, ground control handles it. At really busy airports, you might even need a pre-taxi clearance.
And then ground control for taxi instructions.
Right. Usually request taxi clearance no more than maybe 10 minutes before you plan to move.
When you get that IFR clearance, it can be a mouthful. The CRAFT acronym helps, right?
It does. CRAFT helps you copy it down and read it back correctly. C is for clearance limit, where you're cleared to.
Usually your destination airport.
Often, yeah. R is for route, the specific airways, fixes, or vectors. A is for altitude, initial altitude, maybe expected higher altitude. F is for frequency, the departure control frequency. And T is for transponder code, your squawk code.
And pilots usually know most of that already from their planning, except maybe the squawk code and departure frequency?
Generally, yes.
Yeah.
You filed a route, requested an altitude. Listening to clearance delivery before you call can give you clues about standard routes or altitudes being used.
And writing it down is key, maybe using shorthand.
Absolutely. Develop your own shorthand. Appendix 1 in the source material has examples. It's crucial to accurately copy and read back the clearance. Also, remember, if your clearance includes a published departure procedure, a DP.
You need to have it available either text or graphic.
Correct. And you need to have reviewed it before accepting the clearance. If the DP specifies the initial altitude or departure frequency, the controller might not state those again verbally. They expect you to know it from the DP.
And the golden rule. The last clearance received is the active one.
Absolutely fundamental. If clearance delivery gives you one altitude and then departure control tells you something different, departure control's instruction wins. Always comply with the latest clearance.
What if you call clearance delivery and I say clearance on request?
Just means your flight strip hasn't popped out of the printer or popped up on their screen yet from the center computer. Usually doesn't take long. You can finish pre-flight checks while you wait.
Okay, now the local controller, the person managing the runways, and the immediate airport area.
Right. They manage everything in the Class D airspace, typically, and on the active runways. Some towers are IFR towers, meaning local controllers can issue radar vectors. Others are VFR towers and just handle handoffs from approach.
There's coordination between the tower and the radar facility, the TRACON.
Constant coordination. In fact, towers often release the top part of their Class D airspace, say the top 500 feet, to the radar controllers for smoother handling of overflights.
Interesting. And the tower can't clear an IFR flight for takeoff until
Until they get a release from the departure controller at the TRACON. That controller needs to make sure there's a gap for you in the departure flow. So takeoff clearance depends on that coordination. Next stop, TRACON.
terminal radar approach control. The link between the airport and the en route system. What's their typical airspace?
Generally about a 30 nautical mile radius around the primary airports they serve, and up to around 10,000 feet. But it varies. Class B and C airspace definitions on charts show you the specifics.
And that airspace is divided up.
Into sectors, yeah. Each with its own controller and frequency. You'll usually just call them approach, like Potomac approach or SoCal approach, unless they tell you otherwise.
They're using radar, obviously.
Oh,
Located near the airport.
typically, yes. Figure 2.7 shows an example. And a key thing terminal controllers can do is assign minimum vectoring altitudes MVAs.
Altitudes lower than published procedure minimums.
Correct. They're based on radar coverage and terrain clearance, shown on the controller's scope, but not on pilot charts, like in Figure 2.8.
So if an MVA seems low,
Politely query it. Confirm this is a minimum vectoring altitude, just to be sure.
how does the handoff work from tower to TRACON on departure?
Once you're ready for takeoff, the tower asks TRACON for a release. TRACON confirms they can fit you in. Once you get takeoff clearance and liftoff, departure control is already expecting you.
No need to repeat the whole clearance.
No, just checking. Departure, November 123 Alpha Bravo, leaving 900. They know who you are. Their system usually starts tracking your transponder code automatically once the tower clears you. That's why it's good to keep the transponder on standby until takeoff clearance.
What do they see on their scope for your flight?
A target with a data block showing your call sign, aircraft type, altitude from mode C, and ground speed. They use airport surveillance radar, ASR, for the basic picture, and automated radar terminal systems, ARTS, to process the transponder data. Figure 2-9 illustrates this.
Can they see weather?
Depends on the radar. Older ASR-3, not so much intensity levels, they rely more on pilot reports. Newer ASR-9 can show up to 6 levels of precipitation intensity.
So you can ask them what they're seeing.
Definitely. And pilots of smaller GA aircraft should generally be cautious about flying into anything shown as level 3 or higher. Heavy precipitation can also sometimes block out the data tag on their scope.
You mentioned tech routes earlier. Tower and route control.
Right. Predefined IFR routes entirely within terminal airspace, usually below 10,000 feet. Good for shorter IFR hops between airports within the same large terminal complex, like around LA or New York. Details are in the AFD. Figure 210 gives an idea.
And safety alerts. Any automation.
Yes, a big one is Minimum Safe Altitude Warning, MSIW. The system monitors your altitude and track and alerts the controller if it projects you'll descend below a safe altitude for terrain or obstructions. Especially watchful during rapid descents on approach.
Okay, so after TRACON, we're usually handed off to.
The big guns.
Yeah.
Air Route Traffic Control Center, ARTCC, or just Center.
These cover huge areas, right? Multiple states sometimes.
Exactly. They manage IFR separation in the en route structure, the airways connecting different terminal areas. They use long-range radar, air route surveillance radar, ARSR, mostly tracking transponder returns. Figure 211 shows an ARSRC.
What about their weather displays? Similar to TRACON.
A bit different. Older systems might just show slashes for light moderate rain and H's for moderate heavy, as in Figure 212. Newer ones use shades of blue for intensity levels.
But still limitations.
Yes, the highest intensities can obscure targets, so controllers might not always have the worst weather displayed. And remember the potential time lag in the data feed.
And center airspace is also divided into sectors.
Oh yeah, lots of sectors, often divided into high and low altitude layers. Each sector has its controller team and frequencies. You find these frequencies in the AFD, formatted like Figure 213 shows, and on en route charts.
And because the area is so large, you might talk to the same controller on different frequencies.
Correct. As you fly across their sector, you might switch between different remote transmitter receiver sites they control.
What if you're flying IFR from an airport outside TRACON airspace? Who do you talk to then?
You talk directly to Center for Departure and Arrival Services.
How does that work?
If it's a towered airport, the tower will tell you who to contact after takeoff. If it's non-towered, your clearance from FSS will include instructions like, upon entering controlled airspace, contact Memphis Center on 134.5.
And the key point about terrain clearance here.
Huge point. You are responsible for terrain and obstacle clearance until you reach the controller's minimum vectoring altitude, MVA. Just hearing radar contact from center does not shift that responsibility if you're still below the MVA.
Super important. What if there are obstacles near the departure end?
If a steeper than standard climb is needed, the controller should tell you. But ultimately, it's the pilot's job to check the AFD for any departure path obstacles and be aware. Ask if you're unsure about required climb gradients.
Okay, what about clearances like, when able, proceed direct?
It means use your navigation equipment to fly directly to that fix or navide when you're ready and able. If you get this while VFR, you still own terrain clearance until ATC gives you a specific heading or says proceed direct, and you're above the minimum IFR altitude.
And leaving altitude fly heading or proceed direct when able?
That phrasing specifically keeps terrain clearance responsibility with the pilot until you climb above the minimum IFR altitude for the area. ATC can't clear you below that unless you're VMC and can maintain VMC during the climb.
Are there limitations for center providing approach-departure guidance far from their radar antenna?
Yes. Accuracy decreases with distance. It's harder for them to judge precise headings and distances on their scopes for airports way out near the edge of their coverage. So they'll usually limit their scope range when vectoring to final at distant airports, maybe to 125 miles or less for better precision. You might expect less vectoring overall in those areas.
Okay, let's shift gears slightly to in-flight weather avoidance. ATC helps with that, but it's not their main job.
Exactly. Their number one priority is separating traffic and issuing safety alerts. Weather avoidance assistance is secondary, provided workload, radar limits, and frequency congestion permit.
What can they offer?
They can tell you about areas of weather they see on radar, or maybe chaff. If you ask, they can try to provide vectors or suggest route changes to help you avoid precipitation echoes.
So what can a pilot request?
You can ask to deviate left or right, of course, by a certain number of degrees or miles. You could request an altitude change, or just ask for general assistance. Request vectors around this weather ahead.
But their radar doesn't see everything, right?
Crucially, no. It doesn't see clouds, turbulence, or wind shear directly. It sees precipitation. So getting vectors around the green stuff on their scope doesn't guarantee a smooth ride or avoidance of all hazards.
So if you want to stay, say, 5 miles clear, you need to ask specifically.
Yes. Request deviation 5 miles east, of course, for weather. And very importantly, tell them when you're able to return to your cleared route. Able to resume normal navigation.
And as an IFR pilot, you can't just turn on your own.
Nope. Not unless it's a genuine emergency according to FR 91.3, where immediate deviation is required for safety and there's no time to ask. Otherwise, you must get an amended clearance from ATC before deviating.
So plan ahead if you see weather building.
Definitely. Especially since center radar data can be a few minutes old. Thunderstorms build fast. Try to anticipate and make your request early.
What helps ATC grant your deviation request quickly?
Be specific. Tell them where you want to start the deviation, how far you want to go off course, where you plan to rejoin, whether you're an IMC or VMC if you have onboard radar, and if you might need more deviations later.
Easier to get deviations en route than near busy airports.
Generally, yes. More airspace, less complex traffic flows out in the en-route structure. Terminal airspace can be very constrained. But always ask if you see hazardous weather. Don't just fly into it.
And PIREP's pilot reports are valuable here too.
Incredibly valuable. Tell ATC and FSS what you're actually encountering. Turbulence, intensity, and altitude, icing type and rate, cloud tops and bases, visibility, lightning, hail. It helps everyone build a better picture.
Let's talk more about what ATC does see on their radar weather displays. It's reflected energy from moisture.
That's right. Radar energy bounces off water droplets, ice crystals, hail. The more moisture, or the bigger the particles, the stronger the return signal, measured in dBz.
But they can't tell if it's rain or snow or hail?
Correct. Just the intensity of the reflection. They'll describe intensity using standard terms if their system allows.
Which are?
Light is less than 30 dBz. Moderate is 30 to 40 dBz. Heavy is 40 to 50 dBz. And extreme is over 50 dBz.
But RTCCs don't use light.
Right. Their systems typically filter that out. And if a facility can't determine intensity, they'll just describe the location and say, intensity unknown.
Centers use warp sometimes. Weather and radar processor.
Yes, that mosaics data from multiple NEXRAD sites gives a broader picture, but still has that potential time lag up to 6 minutes. Their backup RSR system shows just 2 levels, moderate and heavy to extreme.
Okay. The materials also define an approach control facility. Is that just another name for TRACON?
Pretty much. TRACON is a type of approach control facility. It's the general term for a terminal ATC facility providing approach and departure services for IFR and VFR flights. They also monitor parallel runway approaches.
And speaking of parallel approaches, there's new tech. Precision Runway Monitor, PRM. What's that for?
PRM allows simultaneous independent instrument approaches to parallel runways that are spaced closer together than the standard separation minimums would normally allow.
How close?
Less than 4,300 feet between center lines, but generally not less than 3,000 feet. Figure 215 shows the setup. It requires special high-update radar, high-res displays for controllers, like in Figure 214, and specially trained controllers.
What's special about the PRM radar?
It's a monopulse secondary surveillance radar, MSSR, that scans electronically, giving a much faster update rate, maybe once per second, compared to several seconds for traditional rotating radar.
Better tracking accuracy.
Much better. It allows the system to predict flight paths more accurately and detect deviations sooner. It tracks transponder-equipped aircraft out over 30 miles and up high, and has visual and audio alerts for controllers.
And there's that critical zone between the runways.
The no transgression zone, or NTZ, a buffer zone between the final approach courses. It's monitored intensely by dedicated PRM monitor controllers, one for each runway usually.
And the system helps them.
Big time. The software tracks each plane, projects its path, and gives immediate alerts if an aircraft even looks like it's going to enter the NTZ. That enhanced monitoring is what makes these close parallel operations safe.
Wow. Okay, wrapping things up, the whole IFR system seems complex but coordinated. Can you walk through the typical sequence of facilities for a standard IFR flight?
Sure. If your prepared frequency's handy, alternates considered, familiar with the route, it's quite flexible. Figure 216 gives a good overview. And always know where the nearest VFR is, just in case.
So for a flight between 2 towered airports?
Typically. FSS for briefing and filing, ATIS at departure airport, clearance delivery for the IFR clearance, ground control for taxi, tower for takeoff, departure control TRACON for initial climb and vectors, ARTCC, center for the en route portion, maybe multiple sectors.
In-flight weather updates.
Could be EFS, flight watch, or HIWAS broadcasts along the way. Then, approaching the destination, ATIS again. Approach control, TRACON, for arrival sequencing and approach clearance. Tower for landing clearance and taxi. And landing cancels your IFR automatically at a powered field.
And if departing from or arriving at a non-towered airport?
Sequence changes a bit.
Oh.
Still FSS for briefing filing, give LATLON for small airports. You'll get your clearance via FSS or maybe Unicom if they have an arrangement, often with a void time. Be ready to copy and depart promptly.
Who do you contact after takeoff?
Directly to ARTCC center, as instructed in your clearance. Then center en route, maybe EFASHUAS. Nearing the destination, approach control for the approach. If you break out into VMC before landing at the non-towered field, you can contact ATC to cancel IFR. Otherwise, it cancels automatically when you land.
One last piece. Letters of agreement, LOAs. What are those?
They're the formal agreements between ATC facilities or sectors that define how they coordinate handoffs, how traffic flows across boundaries, altitudes, routes. It's all spelled out in these LOAs negotiated by facility managers.
Pilots don't see these.
No, the details aren't published for us. That's why the FAA suggests maybe noting on your chart where handoffs typically occur. But rest assured, the controllers know exactly where and when they're supposed to hand you off. It's all pre-coordinated based on these LOAs.
Well, this has been incredibly insightful, a real deep dive into the ATC system. We've covered the equipment, the procedures, the different facilities.
Yeah, quite a journey from the cockpit radio all the way through center control and back down to the approach. Hopefully you, our listener, have a much clearer picture now of this complex system.
And how critical clear communication and pilot preparedness are for making it all work safely.
Absolutely. It's a partnership between technology and human expertise.
It really is. And maybe a final thought to leave you with. Just consider the scale of this operation. Managing thousands of flights daily, constantly evolving. It makes you wonder what the next advancements in automation or integration might look like for air traffic control.
Always something new on the horizon.
Definitely. Thanks for joining us on this deep dive.